In relativity, we learned that physical laws are identical in all inertial reference frames. In fact, that was unsurprising because that's been an assumption of classical mechanics ever since we started learning it. What's more surprising in relativity is that we don't live in a simple world where we have 3 dimensions of space and 1 universal dimension of time. We actually live in a Minkowski spacetime where the concept of space and time and the quantities of space and time can change and move from one to the other as we change inertial reference frames. So particularly as we change between reference frames moving at different velocity with respect to each other, then we follow the Lorentz transforms rather than the Galilean transforms. And one way of encoding that information is that the inner product between 2 4 vectors is not the Euclidean inner product, but in fact this inner product here, where we have a minus sign on each of our spatial components. And so we have a metric that converts vectors into covectors that isn't the identity. It actually has minus signs down the diagonals on the spatial components. So since space-time is not exactly what we thought it used to be, perhaps our physical laws, as we used to write them, aren't necessarily identical in all inertial reference frames, in which case we have to adjust them. Obviously they must be approximately correct in the limit of low velocities, where they've been well tested, but they may not necessarily be correct up at high velocities where the velocities are approaching the speed of light. Now, one way of ensuring that our physical laws do transform in the correct way as we transform between inertial reference frames is to write them down using tensors. Now, tensors are geometric objects that encode physical quantities, and by definition, they transform in the correct way as we go between inertial reference frames. This is the way in which they transform, where these p's here are the partial derivatives between the various coordinate transforms that we might be using. And so far, the only objects that we've discussed in terms of physical laws have been pure vectors. So this is overkill notation for that. For a pure vector, you just have one index up and it transforms like a normal 4 vector. And we saw that energy and momentum could be combined into one 4 vector called energy momentum, and that the total energy momentum was conserved. This is the form momentum for a massive particle, but this final form is in fact true for massive or massless particles, where this is the relativistic momentum, and this term here is always the energy divided by the speed of light. So physically, we've only discussed scalars and 4 vectors. Scalars like proper time, and 4 vectors like space-time position, velocity, acceleration, and form momentum. But in order to examine electromagnetism, which after all is the only classical theory which is already Lorentz invariant, we have to use tensors that are of higher dimension. And so we're going to look a little bit more at tensors and tensor algebra. Now suppose you have one tensor and you have another tensor of exactly the same rank, and you add them together. So they have exactly the same number of vector components and covector components. So if you add the coefficients together, you're going to get another object. And that object is obviously going to have the same number of free indices. And my claim is that this object is still a tensor. How do we show that? We show that by showing that it transforms the right way. Remember, things that transform this way are tensors, and all tensors transform this way. So how do we do that? Well, we know how this transforms and how this transforms. And now, since all of these things are just numbers, we can take out a factor of all these p's. And then this is precisely the c's. And so we have that the c's transform exactly the way they should to be a tensor of exactly the same rank. So if you add 2 tensors, you end up with a tensor. So that was a fairly trivial proof, but there are many other fairly trivial proofs of processes that can create tensors. In particular, outer product and index permutation. The outer product, you just multiply 2 tensors and you just have all their free indices piling up on a third object, and that third object is a tensor. The proof is actually quite easy because if you see how this transforms and how this transforms, you get a bunch of p's from the first object, a bunch of p's from the second object, and they all just gather up, and that's exactly the p's you require in order to get this thing transforming the correct way. And that's even more trivially true of the index permutation. In the index permutation, you just swap 2 of the indices from one tensor and you still end up with a tensor, because when this transforms, you have full product of the list of p's from the indices, and it doesn't matter what order they come in because they're just numbers being multiplied together, and so you show very directly that this is still a tensor. Two more processes that produce tensors are the inner product and contraction. So in both of these cases, we're summing over one index, or at least one index, on the right-hand side between two tensors, and that gives us a tensor. And here we're summing over two indices within a single tensor to give us a tensor. This inner product is exactly the inner product that you would get between, say, a covector and a vector. This is just a generalization of that idea. So the proof that this is a tensor is just a little bit more involved, but not too bad. So first of all, it transforms like that by definition, but we know how each of these transform individually. This is the point at which we're about to make a mistake normally, because if I just use lambda again, then what I'm going to have is I'm going to have a lambda here and a lambda here, and then another lambda. So instead of having two things I'm summing over, I'll actually have four, and that's an indication that I've made a mistake. And so if you do that, you should go back and realize, oh, when I'm doing this kind of expansion here, all of these indices are dummy indices. So I can call them whatever I want. So this second one I'm going to call lambda 2. And because these are just numbers, we can multiply them in any order we like, so we can rearrange. And we already have an identity for the terms in here, because this is just taking the total derivative between the coordinates in the undashed frame and the other coordinates in the undashed frame. And so it's just the delta function. Now, because we've got a delta function, we can actually execute the lambda 2 sum, and it will turn all the lambda 2's into lambdas. And now this is precisely the definition of C in the undashed coordinates. And this is precisely how C is supposed to transform if it's a tensor. And so we've shown that the inner product between two tensors forms a tensor. And finally, there's a special kind of inner product that produces a tensor that's worth mentioning explicitly. And these are special because there's a very real sense in which taking the inner product with the metric gives you the same tensor. So it's the same tensor with just one of its vector components turned into a covector component, or vice versa. And so we might talk about the 4 vector of momentum. If we were to convert that down into a covector, we wouldn't say that isn't the momentum. We just think of it as the same thing in a different form. And so doing that with the metric gives us the same kind of tensor in a different form. But we have to be very careful to mention which indices are up and which indices are down.